In the first part of this section, you learned how to find limits of functions both numerically and graphically. So today we're going to discuss the formal definition. When we finish, you should be able to describe the formal definition in your own words and understand how to use it. You're familiar with the limit notation, the limit as x approaches c, another x value, of a function f of x, is equal to the y value that function approaches, which we call L. Now the formal definition is a biconditional statement. If and only if, given any number epsilon greater than 0, meaning epsilon has to be positive, there exists a corresponding number delta that is also positive, so that if the absolute value of the difference in our x values falls between 0 and the difference between those x's, then the absolute value of the difference between our function and our limit will be smaller than an acceptable epsilon or error that we have chosen. And so I can already hear you saying, you just read it to me and I still don't understand it. I read it to myself, I don't understand it. So let's talk about it a little further so that you have a clear understanding of what this means. Let's say that we want to multiply these two fractions, but we don't want to multiply them as fractions because that's too easy. So let's use decimals. On the left, I have the exact representation of the decimal form of these fractions. And on the right, I have an approximated decimal that I've rounded to 3 decimal places. So I have my exact answer, my L, and my estimated answer, my function. And the difference between these two, taking the absolute value of that, will equal an error in what I have calculated. So in life, we want our errors to be very, very small. For example, if I'm running a bicycle manufacturing plant, and in one of my departments, I make the bolts that hold all the pieces of the bicycle together. So every bolt has a particular size and has to fit the piece it needs to go in. If the diameter is too large, it won't be able to go through the fabricated hole, and therefore you can't put the bicycle together. If the bolt diameter is too small, then the part will fit together loosely and it won't go together correctly and the bicycle will fall apart. So we want to be able to calibrate our machinery within an error because it's machinery, it's going to have some error, but we have to have an acceptable error window where the bolt will still work appropriately. Because if I make bolts that don't work, then I end up having to toss them out and I lose money. So we're looking at the difference between the two x values that we calibrate the machine to. And that difference is our delta. Now look at the symbol. This is the letter delta, where you're used to the triangular symbol delta. Same meaning, two different ways to express it. So what it means is it's the difference between our x values, our x1, which is represented in our formula as x, and then our c, which is actually our x2. So if I make estimated values for the diameter of my bolt, I want them to be as close to the exact value of the diameter that's supposed to go through the whole of the part. So I want to make sure that I know the relationship between the deltas that I choose and the epsilon that's acceptable. If I have a window of an acceptable error, then I know that any diameter of a bolt that falls within that error, it will still be usable. Anything outside that error will have to be tossed. So I want to say that if the difference in my x values is less than delta, then the difference between my function and the actual limit will result less than the error that's acceptable, meaning all the bolts will be acceptable. Now let's do a problem so that you understand this even more clearly. So I have the formal definition of the limit written so that we can follow it like a pattern. we're given the limit as x approaches negative 3 of 1 minus 4x. Now limit notation says limit as x approaches c of f of x. So very clearly, just from my given information, c is negative 3, f of x is 1 minus 4x. My instructions state that they want me to find my limit, L, and then find a value for delta greater than 0 such that the difference between my function and my limit, taking the absolute value, is less than 2, when the absolute value of the difference of my x's falls between 0 and delta. In this line, I can see that they embedded more information where they replaced epsilon with 2. And so I know that epsilon is equal to 2. 2 is an acceptable error. So now we need to find the delta that pairs with that. So our first step in doing that is to find L. We know that we have a function 1 minus 4x and that x is approaching negative 3. So let's plug it in and we get L equals 13. Next, let's use our pattern and set up the problem. Using our given information, we're going to set up what we have and compare it to what we want to get. And so what I'm going to do on the left, I'm always going to be looking over to the right and seeing what do I need to find. So plugging in my information, I have the absolute value of 1 minus 4x, that's my f of x, minus my limit, 13, is less than my epsilon, 2. And my goal is to make it the absolute value of x minus my c, negative 3, so that I can solve for what that will be less than as delta. Doing the math, I simplify, and I look at my pattern. Notice the pattern says 1x to the first power minus c. It doesn't have anything multiplying, but I have a negative 4x. So within the absolute value, I'm going to factor it out. And then we can use that rule of saying as long as I bring it out as an absolute value, I can take it all the way out. And then the absolute value of negative 4 is positive 4. Multiplying both sides by 1/4, I get x minus negative 3 is less than 1/2. And I compare it all the time to what I need, and now I see that it matches. And so I can see my x minus c less than delta 1/2. Therefore, delta is 1/2. Putting it in its formal answer, I have 0 less than the absolute value of x minus negative 3 less than 1/2, which is delta. So what did all of this mean? It means that if I choose numbers for x within 1.5 units of negative 3, then the estimates that I get from my function will be within the allowable error 2 units of L, when L is 13 in this case. So now we're going to be asked to prove it. Proving it is rather simple. We simply start with what we got as an answer, and we work our way backwards, following all of our steps. Because if we can get to our original value of epsilon, then we have proven that as we work through to find delta, that was correct as well. So we're simply going backwards. How did we get to x minus negative 3 less than 1/2? We had multiplied both sides by 1/4. So the opposite, multiply both sides by 4. And then where did that 4 come from? It had come out of an absolute value, having been negative inside. So we put that back and we distribute it back through. And when we do that, we get right back to our absolute value of the difference between our actual function and our limit, and that's less than our epsilon 2. Now look at all the work we just did. If I actually run a factory, then that means that for everything I make, I'm going to have to do this over and over and over. That's not acceptable. We need to use our time more wisely. So we're going to come up with a more general form. So looking at the exact same example, but this time we're going to ignore our error value. We're going to use epsilon as a variable and leave it as a variable, so that way, depending on what I'm making, as the error acceptability changes, I can change that within my formula. So again, what we have and what we need, And we set it up exactly the same way. The only difference this time is that epsilon is remaining a variable. And so as we work through, we keep going until we actually see it match what we need, and we get to that point, then we can see a very clear relationship between delta and epsilon. And then we have to prove it. So we start working backwards and prove that we solved for delta correctly by undoing all of our steps. And when we get to the end, it's perfect. Now it's your turn to show me what you know. Describe the formal definition in your own words. If there's any areas that are still unclear, make sure that you include those questions in your description. And then we'll discuss this and do more problems in class tomorrow. All of these submissions are due in my Google Form box by 6:30 tomorrow morning. Your assignment, you'll have 2 days to work on this, and make sure you check the calendar so that you know when the next video will occur.